In mining, we are interested in the minerals, the metals, and the ores. Minerals are naturally inorganic substances possessing definite chemical compositions and atomic structures. Definite chemical compositions and atomic structures. Now, it's very important you note that if the minerals containing the important metals were uniformly distributed throughout the earth, they will be so thinly dispersed that their economic extraction would be impossible. Now, the occurrence of minerals in nature is regulated by some geological conditions due to the action of precipitation, weathering, alluvial movement, and crystallization. Minerals deposits are found in sufficient concentrations to enable the metals to be profitably recovered. So looking at the ore is just but a natural aggregation of minerals from which a metallic or non-metallic compound can be recovered, and not just recovered, with profit. It's very important. And they can be classified according to the nature of the valuable mineral, and they can be classified by the nature of their gangues and according to the use of the mineral in question. Then we could look at the nature of the valuable minerals. We have the native ores, which are the metals in their elementary form. Then we have the sulfide ores, which are the metals in their sulfide form. Then we have the oxide ores, metals in their oxide form. Then we have the complex ores, which could have a combination of the earlier mentioned. So we have also, by the nature of their gangues, we have the calcareous or basic, okay, which are usually lime rich. Then we have the siliceous or acidic, which are silica rich. So, and another classification according to the use of the mineral, we have the metallic ore and the non-metallic ore. And most ores are mixtures of extractable minerals and gangue. And the gangue is actually extraneous rocky materials, the unwanted parts, those additions that came with the ore, they are the gangue. Okay, so native metals can be used directly, their elementary forms can be used directly, and then others have to be beneficiated, that is concentrated, or you can say processed. Okay, and also treated metallurgically. So we also have according to the metallic aspect of the mining, so we have classifications of the metals into grade. So the grade is just an assay, is the percentage of the element or compound of marketable end product, and grade is just a measure of the quality of the ore or the concentrate. Now, for high grade ores, the valuable mineral assay or the valuable mineral grade is expressed as percentage of metal. For high grade ores, they are expressed as percentage of the metal. Example, if we have iron ore, let's say 50% iron, okay, so this is a high grade ore. And then let's say for copper ore, then we have 3% copper, right? So it's expressed as percentage of the metal for high grade ores. So for low grade ores, we could have the valuable mineral assay expressed as parts per million or gram per ton. So example is the gold ore, which is a valuable mineral. So we could express it as low grade ore to be, let's say for example, 5 gram per ton gold, or we can say 5 parts per million gold. So then we have some metals that are in their solid, they are solid in their oxide form. Thus, their grade is expressed in terms of their oxide content. Yeah, so we could have percentage tungsten. All right, we could have percentage uranium. The oxide of uranium, the oxide of tungsten. We can have the oxide, percentage oxide of chromite, which is the ore. We can have the percentage of the phosphate, which is the oxide of phosphorus, and so forth. So we have the non-metallic minerals. These are under grading, and it is graded as their mineral percentage. All right, so we can have percentage of barium sulfate. All right, or we can have the percentage of calcium fluoride. These are different ores expressed as their mineral percentage. They are non-metallic. So we have another grade, the diamond. It is exclusively diamond. So this grade is expressed as carat. It's only diamond that is expressed as carat, and that's the grade. So we could have, let's say 1 carat is 0.2 gram, and then we have coal. Coal grade is expressed as ash percent or percentage ash, or you could express it as calorific value, that is kilocalorie per kilogram. That's the unit, right? Now it's actually also important that you note that the minimum metal grade required for a deposit to qualify as an ore varies from metal to metal and from time to time. Let me give you an example. The non-ferrous ores may contain as little as 1% metal and often less. All right. Gold may be recovered profitably in ores containing only 5 parts per million, and iron ores containing, let's say, less than 15% iron are regarded as low grade. Now when ores are being mined, they are mined as run of mine, ROM, and these are ores consisting of valuable mineral and gangue. They are called the run of mine. All right, and we have to undergo what's called mineral processing, which prepares the ore for extraction of the valuable metal. All right, so mineral processing is just a physical process for separating the valuable minerals from the gangue. All right, so once the run of mine is being fed or being changed into different forms, different stages of the mineral processing, what you're going to have as the end product is what is called a concentrate. All right, the concentrate is the enriched portion of the valuable mineral. Then we also have a tailing. You have a product, you have products, the concentrate and the tailing. The tailing is the gangue, or those waste product, let's say waste product or discarded materials that are unwanted in the concentrate. All right, and you should also note that the mineral processing does not destroy the chemical and physical identity of the mineral. All right, and mineral processing is, you could also term mineral processing to be ore dressing or beneficiation. These are all used interchangeably to mean the same thing. It is also called mineral processing. All right, So, and you need to also know that. So you need to also know that the ore of mine undergoes different stages before the concentrate or the tailing is achieved. And if you look at those flow sheets, you get to see the various stages which we're just going to discuss now. So if you look at the photograph attached in this video, you can see some of the many minerals that are mined and processed. You know, mineral processing is involved in the production of actually three main products, and these three main products are the aggregates. Okay, then we have the minerals, then we have coal. All right, the aggregate is maybe stone, rock, and minerals are those element, gold, for example, iron, lead. Then we have coal. So these are the um, production of the products, the three main products in mineral processing. Okay, so mineral processing is also used in the recycling industry, and there are actually four main steps in mineral processing. We have the first step to be the characterization, then we have liberation, we have separation, then we have disposition. All right, so in order to make you understand fully, characterization is actually the first step in mineral processing, and it's when the mineral is being processed, um, it's identified, okay, and its chemical physical properties are also noted. So it's all about identifying and noting the chemical and physical properties. All right, that is characterization. And characterization actually answers two basic questions, like what am I processing, and what property can I use to help the process, help process the material. So in the characterization step, sampling is often performed. Then sampling answers the first question, what am I processing? All right. So, and there are a variety of sampling techniques, but each involves taking a representative sample which is analyzed to identify the components of the feed material. You see, this is all about the physical aspect of it. So when the feed material is identified, important chemical physical properties of the materials can then be identified. Now, the most important property is size. That is the most important property. It's a physical property. Now, other important properties are magnetic susceptibility and electrical conductivity, and then we also have density. Okay, so we have the second step in mineral processing, which is liberation, and it's just the process where the similar elements in the feed material are freed from one another. They are being liberated, they are being freed from one another, and this is often accomplished by size reduction. So size reduction has to do with crushing and grinding. We can call that comminution. Okay, that is crushing and grinding. Now there are two classes of size reduction machines which we will look at, and in order to liberate these materials from each other. So we have the crushers and the grinders. So the crushers deal with large particles, usually particles greater than, let's say, 1 millimeter in diameter, while the grinders deal with particles smaller than 1 millimeter in diameter. All right, so in a nutshell, the crushers actually handles particles larger than 1 millimeter in diameter, while the grinders handle particles smaller than 1 millimeter in diameter. And there are two types of crushers we have, but all either crush by either compression or impact. Those are the method of crushing by these crushers, by compression or impact. So particles can actually be compressed or impacted until they break into smaller pieces. All right. Now, typical crushers have a reduction ratio of 40:6. And what this means is that if you put, let's say, a 40 millimeter diameter particle in them, they will give you a range of particles of about 6 millimeter in diameter, and that's very, very much, effective. You could look at this diagram here of a particular type of crusher. We call this crusher, look at it closely, it looks like a jaw. So this is a jaw crusher. It uses compression to crush the material, okay? And then as with crushers, there are a variety of grinders, okay? So, but they all use the same concept for grinding. They either have the feed particles smash against themselves, or the feed particles smash against stronger material in for size reduction. So when these feed particles grind against themselves is what you call autogenous mill. So, but when the particles grind against a stronger material, all right, it is called a ball or rod mill. All right. So depending on the shape of the stronger material used, all right. So when you look at this picture here, you could see this is a picture of how a ball mill works. You can see over there. So, and now in the mineral processing industry, it has actually created what we call a work index value. And the work index value helps us to understand the hardness of the feed material. All right. The index assigns values to minerals based on their difficulty to grind. So we could therefore say a high work index means that the mineral is hard to grind. And then the coal industry also assigns value based on the coal's hardness. Yeah, that's an example. And this time the value is called the hard groove grindability. Okay, but however, in the hard groove grindability um, index, higher values signify softer, easily ground coal. So in a nutshell, a work index value signifies higher values. It shows that the higher values are harder to grind, but the hard groove grindability shows that higher values are softer and easier to grind. Then we have the next stage, which is called the separation. All right. So it's actually the most important step in the mineral processing. So it is when the different components of the feed materials are separated from each other. So, and the separation uses chemical and physical properties to achieve this. All right, because particles are most often separated by size, density, magnetic susceptibility, and electrical conductivity, as I've mentioned earlier. So aggregate mineral processing usually skips this step and continues directly to disposition. All right, but size separation is primarily done by screening. Okay, you could refer to the flowchart where we talked about screening there. All right, so you can see this image here. Is an image of series of different mesh sizes called screens. Okay, so screening is often done in series, so multiple streams of different size ranges can be created. And there are two types of mesh sizing. We have the Tyler and the US series. In both systems, larger mesh sizes correspond to smaller hole sizes. Okay, so and then we have the density separation. and it's performed by what we call the hydroclones or the dense medium separations. Okay, now the dense media separation involves pouring the material in a specially prepared fluid that has a density between the components of the feed materials. All right, now this material that floats, all right, has a lower density than the fluid, right? While materials that sink has a density greater than the fluid. And you could see in this picture here, it shows how the particles react in a dense separation. Now the hydroclones work on the same premise as dense media separators, okay? But the material here and the prepared fluid are spun, all right, around utilizing what we call the centrifugal forces, all right? And then the feed material that comes out of the top of the hydroclone is less dense material, and the feed material that comes out the bottom of the hydroclone is the dense material. You can also see it in this figure. It is an image of how a hydroclone works. So the hydroclones are used extensively with feed particles smaller than 100 micrometer in diameter, while the dense media separation is used with larger particles, all right? Then the hydroclones are used with smaller particles, all right? Because small particles need this centrifugal force to speed separation, all right? Now, magnetic susceptibility separation is done by exposing the feed to a magnet, right? Feed material that is attracted to magnet is magnetic and falls into one bin or into a particular portion, all right? While feed materials that is unaffected by the magnetic or media is non-magnetic, since they are not affected, so they fall into a different column. So magnetic materials include, iron, magnetite. You can see in this figure here, it shows how the process of magnetic susceptibility separation actually works. You can see here, you see some non-magnetic materials that falls away, and the ones that are being retained by the attraction of the magnet. So we also have electrical conductivity separation, and it is achieved by using what we call a high tension separator. All right, now a high tension separator charges the feed particles. Okay, it charges them, the feed particles becomes charged. All right, the feed particles that retain an electric charge fall into a particular column, while those that do not fall into a separate column, and that is how they are separated. So depending on which the column the particles fall into, it is classified as a conductor or a resistor. Okay, so the conductors retain the electric charge. Examples are the copper, iron, aluminum, and the rest. So while we have the resistors that do not hold an electric charge, all right, we have maybe plastic, soil, lead. And then if you look at this picture too, you could see how it works. All right, so that is all about the electrical conductivity. Then we have finally the disposition. Is actually the final step in mineral processing. So it entails the removal of waste, in an environmentally acceptable manner, and the sale of the product. So okay, so this is actually the removal. This is where you have to talk about, you remember the last stage, which is the concentrate and the tailings. This is the final stage in the mineral processing.